7.3, we're going to study something called polar coordinates. This is just a different way to find a spot on the plane, or when you get into Calc 3, you'll be doing this in 3 dimensions with another little bit added. Okay, so normally we graph things in rectangular coordinates, whereas this is, it's kind of like take this many blocks east or west, and then this many blocks north or south. Now, with polar coordinates, we're looking at it more like as the crow flies. R radius will be the distance from the origin, whereas theta is how far you have rotated from standard position, the positive x-axis. You rotate through theta, and along that line, that direction line, you're going to move from the origin out r units. So whereas with rectangular, you're going to go this many in the x direction and that many in the y, now it's a straight shot, like as the crow flies, like I said. Okay, plotting points in polar coordinates. This point right here says rotate out to pi over 3 degrees from standard position. So I'm going to rotate out 60 degrees, pi over 3 radians, sorry, 60 degrees, and then I'm going to move 3 units out from the origin. So now with rectangular, we could say 1, 2, 3, and 1, 2, 3. But in polar, we're not using or squares, we're using circles, okay? So if you imagine a circle with 3 units, you've got 3 up, 3 down, 3 over, 3 out, back, and you see that circle, your point is going to be on that circle at 60 degrees rotation. All right, look at this guy. We're going to go all the way from 0 over to 7 pi over 6, and we're going to move out 2 units. Here you can rotate minus, so I'm going to go negative pi over 3, negative 60 degrees, and move out 2 units. You can also have a negative radius. So I'm going to rotate to 2 pi over 3, and then along that radial line, I'm going to go backwards 3 units. So you see this point is the same as minus pi over 3 with r positive, right? So the same point can be written in different ways. This is the same, like I said, as going out 3 units from the origin in the direction of minus pi over 3. You can also go out 3 units and go all the way around this way, which would be 5 pi over 3. Many ways to write the same points, but your standard way would be the quickest and easiest way, right? So there's some examples of plotting points in polar. Now, if you're given a point in rectangular and you have to convert to polar, and this is something you will have to do, then remember the distance for it's just the Pythagorean theorem, right? The distance from the origin squared would be the hypotenuse squared. And you're just going to square the horizontal, square the vertical, add them together, take the square root, you get the r. Also, think about it, when we're rotating out to theta degrees, and we're going out r units. All right, here is your x distance, and here is your y distance, right? So we have this right triangle, and you see it's very simple to see this. Pythagorean theorem, hold on a second. This is x, y, which is equal to r theta, right? Same point. But that angle theta in there, r is the hypotenuse, and the y is the opposite, The x is the adjacent. So if I know x and y, I know the tangent of theta. So I'm just going to invert the tangent to get this theta. Now, pay attention to the signs of your x and y values to make sure that you get theta in the right quadrant. The inverse sign on your calculator is only going to give minus pi over 2 to plus pi over 2. If you had a negative x and a positive y, you'd be in quadrant 2. You'd have to adjust because the calculator is going to give it to you here. If you have a point where x and y are both negative in quadrant 3, the calculator is going to give you quadrant 1. So you have to pay attention to what quadrant you're in. You might want to write that down before you start doing this process and make sure that you adjust that angle accordingly. Now, if we're given our theta and we want to convert to xy, we know that the x value is the adjacent, so r times the cosine, hypotenuse times adjacent over hypotenuse, right? You get just the horizontal, and then the same thing with the sine for y. So a couple of examples worked out. If we're given 3/5, that's in quadrant 1. So we know that the angle that my calculator gives me is going to be correct. So to find the radius, we're going to square it, add them together. R is the square root of that. The direction angle, y over x, is the tangent. So the inverse tangent of y over x, stick it in your calculator. It's going to give you your answer in quadrant 1, so we're just going to go with it. All right? And whether we're using degrees or radians depends on the situation. If I did this process in radians, then I would get some awful decimal value, and so I'd rather just use degrees. For polar converting to rectangular, we have the hypotenuse, right? And we have our angle of rotation. So x is our cosine theta, y is our sine theta. We just happen to, this is a common angle. So we know that the sine and the cosine are the same, and we get our answers. All right, doing equations can be a little bit harder. Well, no, it is a little bit harder. Recognizing that this equation in rectangular is actually a circle centered at the origin with a radius of 5. Obviously, isn't that cool that that's the equation though? There's no theta dependence because you just have radius equals 5 and you're graphing all the points that satisfy that. So you're just going to go all the way around through all of the angles 5 units from the origin. Now, the way to do it is to recognize that x squared plus y squared is r squared, and you take the square root. Now, we normally want our radius to be a positive value, okay? And when you do take the square root, you're going to get the absolute value in this case. All right, what if we were not centered at 0? We can FOIL this thing out and get this. If we put x squared plus y squared together, that's r squared. X is r cosine theta, so replace that. Now look at this equation. It equals 0 because the 4's canceled. So if this equation equals 0, we can factor out the r. Here's what's left. Set each of those equal to 0. Now r equals 0 is just a point at the origin. And I want you to notice that if you plugged, if you set this thing r equal to 0, you're going to get a point on this graph, right? So this point is on the graph of this. So this is good enough. When cosine of pi over 2 or 3 pi over 2, those are zeros. So you will pass through the origin by graphing this. So that equation is enough. A few more examples. If we have a simple straight line and we want to convert to polar, we're going to replace the x with the r cosine. replace the y with r sine. Now I can factor an r out of this equation and get this, right? R is what you want to solve for when you're getting an equation in polar. So I'm just going to divide both sides by this thing. This is horrifyingly nasty, but it's just a straight line. Isn't that crazy? So in the real world, you'd choose to use rectangular. Um, for the line y equals 5, this is just a horizontal line, right? We're going to replace the y with r sine and solve for r, and we get a simple equation. This is good enough. If you were graphing it, you'd want to use this equation just because, right? Okay. What about x squared equals 3y? Replacing x with r cosine gives me r squared cosine squared. Replacing y with r sine. Get everybody on one side, factor out the r. I'm going to get r equals 0, and I'm going to get this thing equals 0, which gives me that ugly piece of equation right there. And all I did down here was say sine over cosine times 1 over cosine. It gives me secant tangent. Now, r equals 0 is one of those equations. Is that on the graph of this? Well, when theta equals 0 or 2 pi, this is a 0 and this is a 1. So yes, this is on the graph of this. So we're confident that this is a good enough equation, or even this. Okay, here's a special case. We know that x is r cosine theta. So if I multiply this equation both sides by r, I get r squared, which is x squared plus y squared. And now r cosine theta gets replaced with an x. So now I've eliminated all of my r's and thetas, but this isn't very pretty, right? And what the heck does that graph look like? So I'm going to move the 4x over to the other side. I'm going to look at just this bit and complete the square. So half of 4 is 2, so I write it down, square it, put a plus in front of it, but I have to do that same thing to both sides of the equal sign. Now this, I have created a perfect square. It looks like this. And now you see I have the circle centered at 2, 0, radius 2. And I've gone from polar to rectangular. Now, what if r equals 3? Well, square both sides, boom, and we get r squared is x squared plus y squared. We recognize this as the circle with radius 3. We recognize this as the circle centered at the origin, radius 3. Okay, what about this line? If I know that theta equals pi over 3, think about what that's going to look like. If I have just this, and I don't have any dependence on the radius, so any distance from the origin is fine, but I just have this radial line where the angle is pi over 3, 2 pi over 3, then I have a straight line that's at a 60-degree tilt below, I don't know how to say this, below the x-axis, right? So there's a particular slope there, and my y-intercept is at 0. So here's what I want to do. I know that tangent of theta will be y over x. So if I take the tangent of both sides, I just get a number over here. It's minus root 3. So y over x equals minus root 3. Boom. Y equals mx plus the y-intercept is 0. So isn't that awesome? All right, next example. I know r squared, and I have to use an identity for the sine of 2 theta. So I'm going to first use the identity, but then look at this. With a sine here and a cosine here, to change to x's and y's, I need r sine and r cosine. Well, I have r times r right here. So take one of those and multiply the sine. Take the other one and multiply the cosine. That's yx. So 2, first of all, I'm just going to divide away the 2. I get y times x equals 2, y equals 2 over x. Awesome, awesome. What about this guy right here? Secant is 1 over the cosine. So if I multiply both sides of this equation by cosine, I get r cosine theta equals 6, x equals 6. So practice, 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 right? This equation right here, if I multiply both sides by r squared is easy to convert, and I'm going to distribute the r through here. That gives me x, that gives me y, and I have this equation. Now, I recognize that that's a circle because the x and y are both squared with the same coefficients, same signs. That means it's a circle. But if I really want to dig deep into this, I'm going to move that 8x over to be with this, move the 5y over to be with the y squared. I'm going to complete the squared. Half of the 8 is 4, square it and add it to both sides. Half of 5 is 5 halves. Square it, put a plus in front of it on both sides. Calculate this, and you get your radius squared. Write these two things as perfect squares, and you can find your center. So you have a circle centered at 4, negative 5 halves, with a radius of square root of 89 over 2. All right, this is covered in 7.4, but I wanted to give you a little taste of it. By the way, go to section 7.4, and in that section, you'll see a whole chart that shows you forms of polar equations and their graphs. And you're going to get flowers and curlicues and hearts and spirals, all kinds of really cool stuff. So check that out, but I want to give you just a quick example here. Now, if this is my equation, instead of converting this to rectangular and seeing that it's a circle, I want to plug in values of theta to figure out what my radius is. And then on a grid, I'm going to rotate to whatever the theta was, and then move out that many units from 0, or from the origin in that direction. So whenever you're graphing in polar, you want to have radial lines for your angles, and you want to have circles that show a distance from the origin. I am so bad at this. That's too far out, but whatever. So concentric circles that show these circles are not really circles, but you get the idea. Show a distance from 0 or from the origin. And then we'll put our radial lines in after we've calculated our values. So notice that the angles that I chose to plug in, I stopped at pi. We'll just see what happens. We'll find more points if we need to. But notice that the cosine at a 30-degree angle, the cosine would be root 3 over 2. That's a pain in the neck. So I chose the angles that are going to give me 1/2 because they're easier, okay? That's all. That's the only reason, because it's easier. Cosine of 0 is 1. Cosine of pi over 3 is 1/2. Cosine of pi over 2 is 0. Cosine of 2 pi over 3 is minus 1/2. Cosine of pi is -1. Now I'm only halfway around, but let's see what happens. Now to find r, I'm going to take the values of those cosines and multiply by 3. Now when I am plotting these points, plotting the points is easy. When I start connecting the dots, I have to stay within the wedge that I'm passing through. So pi over 3, 2 pi over 3, and then we're going to just stay there on the top, but I want you to see sometimes my radius is negative, so I'm going to stay within the wedge but then go backwards. Does that make sense? So when I'm at 0, my radius is 3. So on the 0 line, I'm going to go out 1, 2, 3 units. When I rotate from 0 to pi over 3, all of my points have to be within this wedge, but I'm going to go down to 1.5. So on that pi over 3 radial line, I'm at 3/2, which is right there. So graphing the point from this point to this point, rotating through in that wedge. Okay, now I know it's going to go like that. This is as far away as I can get, right, when the cosine is 1. So all of the points from this point to this point are going to be within this circle, smaller than that. So I'm not going to go out like that. I have to stay within. Let's get this part done. And then rotating through this wedge right here from pi over 3 to pi over 2, I'm going from 1.5 to 0, but I have to stay within this wedge. So I've got to go from here to here within that wedge. So don't touch the y-axis until you get right there. So there's the first little bit. Now from pi over 2 to 2 pi over 3 in this wedge right here, I'm going from the origin to a negative radius, which means in this wedge, all of my values are negative, which puts me in this wedge for my points. And I'm going out to 1.5 backwards, right? All my points have to be within that wedge. And now from 2 pi over 3 to pi, I'm in this wedge, but all of my values are negative. So the opposite of this wedge, or the negative of it, is going to be here. So all of my points connecting this to this have to be within this, and I don't touch this radius until I get all the way to that point. And I have a circle that's actually centered at 1.5 with a radius of 1.5. To show that that's the way it is, I can take this equation right here and I can multiply both sides by r. R squared is x squared plus y squared. I'm going to move the 3, r, the cosine theta is x. X squared minus 3x. Take half of 3, square it, and add it to both sides of the equal sign. Don't forget there's still plus y squared. So this gives me x minus 3/2, perfect square, plus y minus 0 squared equals radius squared. The circle centered at positive 3/2 with a radius of 3/2. So you see that we're right. So the graphing is in 7.4, and it's actually not in the outline for this course, but I needed to show you this You will learn how to do this when you get to Calc 3. And like I said, there's different forms of this, and you can draw flowers with lots of petals. You can get circles like this. You can get hearts and all kinds of really cool things. So just look through the section 7.4, look for that chart so that you can see all the cool stuff you can do by graphing in polar coordinates. This was section 7.3. Get that homework done.